G'day folks. Today we're going to introduce a new idea. Pretty simple, pretty straightforward. It's just a matter of extending a definition of something that we already know. So what's the thing that we already know? Well, when we're talking about trigonometry, we begin, like our whole study of trigonometry, after Pythagoras' theorem, we begin our study of trigonometry by looking at the trig ratios. We start by looking at sine, cos and tan. Okay, most recently we've been introduced to sec, cosec and cotan as well, which are the reciprocal ratios. But remember we started off by looking at, you've got a right angle triangle, there's your theta, there's an opposite, an adjacent and a hypotenuse. And we said, the sine theta was the opposite over the hypotenuse, cos theta was the adjacent over the hypotenuse, tan theta was the opposite over the adjacent. Then we extended that to say, well, what happens if we have these upside down? And so we had cosec theta was the hypotenuse over the opposite, sec theta was the hypotenuse over the adjacent, cot theta was the adjacent over the opposite. And we saw relationships that existed between those. For example, if you get sine theta divided by cos theta, O over H divided by A over H, you get O over A, so sine theta over cos theta was tan theta. So trigonometry begins with those definitions. You start with a right angled triangle, and you identify the sides, and you realise that there's ratios that exist between the sides and you name them. Okay. There's restrictions with this definition, right? What are the restrictions? Well, in a right angled triangle, it's necessary that these other two angles are always going to be acute angles. Right? You've got a right angle in a triangle, well that's 90 degrees. The other two angles need to add together to make 90 degrees. So by definition, no, not just by definition, but by the actual reality of what a triangle is, those angles must be less than 90 degrees. Okay. So it's more than just by definition, okay? It's by a definition is something that we impose. This is a reality that we recognise. These must be acute angles. But there's another way of defining, sine and cosine and tan, and then by extension, realising that cosec is 1 over sine and sec is 1 over cos and cot is 1 over tan. There's another way of defining those things that take us out beyond just a right angle, beyond just angles in acute angles. I'll get my tongue out of my eye so I can see what I'm saying. They take us beyond acute angles inside a right angle triangle. Okay, so what's this other way of looking at them? Well, allow me to introduce this idea known as the general angle. Okay, so we're not going to start with a triangle now. Instead, we're going to start with a number plane. Okay, and we're going to define the positive x-axis as 0 degrees. Right? So in other words, starting at the origin, going out horizontally on the x-axis, I'm going out at an angle of 0 degrees. Okay. Well, and then I'm going to open up into that sort of first positive quadrant. So remember, this is not exactly arbitrary. I mean, it kind of is, but it's not exactly arbitrary. Remember way back in year 8 when your teacher got you to draw up a number plane and you played Battleship for the first time? Okay. Your number plane started off with 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3, negative 1, negative 2, negative 3. Like, the first place we learnt about coordinates was here, right? In this region here, right? Where both our x and our y coordinates were positive. Right? Then we extended that out, right? We were always familiar with a negative x-axis from when we did integers, directed numbers back in year 7. So this was what we used to call our first quadrant. That's where we began. So extending around, if that was number 1, and this was the second quadrant, this here is the third quadrant, this is the fourth quadrant. So there's kind of a logic in in starting here at 0 and then going around into this quadrant first. Right? This is our first quadrant. And beginning there, if I follow my first quadrant around, well then the y-axis is going to be 90 degrees. And into my second quadrant, I end up with the negative x-axis being 180 degrees. And into my third quadrant, I'm down here at 270 degrees. And then back around here, I'm at 360 degrees. So it's a lot like bearings, but with bearings we start off with north being 0, okay? Now we don't start with north being 0, we start with the positive x-axis being 0. And with bearings we started with north being 0 and we went clockwise around. Now we start with the positive x-axis and we go counterclockwise around, okay? So it's just another convention that you're going to need to get yourselves used to, okay? So this opens up a whole world of more angles. Now, nothing stops me from going first quadrant, second quadrant, third quadrant, fourth quadrant, fifth quadrant, sixth quadrant, seventh quadrant, eighth quadrant. If Mr. Obeid was to stand here and jump around and do a spinning kick, I'm not going to because I don't want to kick the camera or hurt myself. But if I was to stand here and jump around and do a full-on 360 and I landed back here, you'd say, wow, Mr. Obeid did a 360 on camera, you know, like it's immortalised forever on YouTube. Well, what about if I really put some oomph into it and I jumped around and instead of just doing a 360, I went beyond 360 degrees? What happens if I went around to 450 degrees? Well, I've spun into, you know, here I go, first quadrant, second quadrant, third quadrant, fourth quadrant, fifth quadrant. I'm going through more and more quadrants, right? So I could keep on going. Fifth quadrant, sixth quadrant, seventh quadrant, eighth quadrant, okay? And that'd be, as well as being 90, that'd be 450, and then if I went again, it'd be, 540, etc., all the way around 720 when I got back here again. I can even go backwards. Right? So, sorry, I should have labelled this one, fourth quadrant. But I can even go backwards. Now, this is going to sound like a weird way to think about it, but keep this one up your sleeve. When we look at trigonometric equations down the track, you're going to thank me for introducing this idea now and not then, because then it's going to sound very confusing to you. So if I was to go backwards, if this is where I begin, so from 0, if I go up from here, well, if I was to go backwards, another way to think about this quadrant is, and this is a Mr. Obeidism, I haven't read this in a textbook anywhere else, but it's a good way to think about it. I call this the -1th quadrant. And this the -2th quadrant. Minus first and minus second sounds dumb. I know -1th sounds dumb and -2th sounds dumb, but it sounds a lot more sensible to me. Quadrant, sorry. This would be the -3rd or -3rd quadrant. And that's the -4th quadrant. Okay. That's not going to come up an awful lot, that -1th, -2th, -3rd, it's not going to come up a heck of a lot, but it's going to come up, and when it does, you're going to be very, very, very grateful that you've seen this idea now. Okay. So, where is sine, cos and tan gone? Okay, well, hang on a second. Imagine if I drew a circle in here that had a radius of 1 unit. I draw a circle with a radius of 1 unit. Okay. And then from the origin, I had some ray coming out to intersect with that circle. And that ray made an angle of theta. Now, remember how we started with this being 0, and that 90, and that 180, and 270, and 360? All of these angles are measured from the positive x-axis. So if I wanted to go up, say, 45 degrees, well, I go there. If I want to go up 80 degrees, I go there. If I want to go up 90 degrees, I go there. If I want to go 110 degrees, I go there. I go from 0, I go around to 100 degrees, or around to 150 degrees, or around to 180, or around to 200, or around to 270, or around to 300, or around to 360. Okay, I'm going from the positive x-axis. Okay, so if I was to draw that ray there at an angle of theta, well, look at this triangle that we make here. Now that triangle has got a horizontal component to it that I'm going to call the x component for obvious reasons, and it's got a y component to it. And the hypotenuse of that triangle is 1. Well, think about what I know. Think about what I know. I know that the sine of theta is equal to the opposite over the hypotenuse. The cos of theta is equal to the adjacent over the hypotenuse. The tan of theta equals the opposite over the adjacent. Okay, and likewise, by extension, cosec of theta is 1 over y, sec of theta is 1 over x, cot of theta is x over y. Okay, so by extension, we can go into the reciprocal ratios as well. I'm not going to do that right now. I don't want to just sort of burden you like right just this second with it. But now we've got another way of thinking about the trig ratios, and we can define the ratios for any angle. We're not restricted to defining the ratios in terms of acute angles between 0 and 90. Okay, so I can say to you, for example, you know, let me actually come up with a numerical example, and then we'll look at how that relates to the diagram. So give me a moment, I'll just clean the board down and we'll come back. So if you're interested in getting some notes down, what you see on the board right there is a really, really good thing to keep for your records. You might want to sort of hit pause and get all that down. I'm going to clean the board and I'll be right back and we'll look at some numerical examples of how this applies. Okay, so don't go anywhere. Magic of YouTube, I'm going to be right back. Okay, welcome back. I should have done one little tiny extension on the diagram I had on the board in the last bit. It's a very minute one, but watch, you'll see it's not going to be that difficult. Let's pretend that I'm not talking about the unit circle anymore. I'm not talking about a circle of radius 1. Let's say I'm speaking about something more general, something with radius r units. So it goes out to r, up to r there, down to negative r there, and down to negative r there. Okay. Well, still I've still got my triangle defined exactly the same way. That comes out at an x distance, that goes up a y distance. Now sine theta is going to be opposite over hypotenuse. Well, my hypotenuse isn't 1 anymore, my hypotenuse is r. Right? Likewise, cos of theta is adjacent over hypotenuse, x over r. Tan theta remains the same, tan theta is still x over y. So just introducing that r, just so some of these numerical examples I've come up with here work out a little bit nicer for us, okay? So if you want to augment, if you like, the drawing you had from the last board, you can include that for a more general size circle. All right, let's look at this example here. I want to know what sine, cos and tan of theta are down in my circle over here. I've got a circle with radius 5 units. and theta is on a ray such that it makes, it intersects the circle at the point 3, 4. Okay, 3, 4, 5. That's, I mean, the reason why we wanted a radius of 5 is because we get nice numbers for our triangle. So that's certainly a right angle, we know that, no doubt about it. I want to know what sine, cos and tan are. Well, remember sine theta is y over r. So the sine of theta here is 4 over 5. Because remember the radius of my circle is 5 units. So sine theta is 4/5. What about cos theta? Cos theta is the adjacent over the hypotenuse. That's 3 over 5. Okay. And tan theta is x over y, so it's going to be 3 over 4. Very straightforward. When you've got the three sides of your triangle, it's a piece of cake. But that's not why we're doing this. We could have done this without any of this sort of circle nonsense. We could have done it back when we had good old-fashioned acute angle triangles. Okay, so let's extend it a little bit more. Let's look at this guy over here. Okay, this time I've got a circle with a radius of 13. Okay, so we go 13, 13, negative 13, negative 13, and we've got theta such that it's intersecting our circle around here at negative 1, 12. Okay, so that's the point negative 1, 12. I want to know what sine theta, cos theta and tan theta are. Okay, it's outside of a right angle triangle. I don't have an opposite and an adjacent that I can use nicely. But that's okay because I can use my definitions. Over here, sine of theta is y over r, cos of theta is x over r, and tan of theta is x on y. So what is y over r? Well, y over r, my y value is 12, over my radius is 13, so it's 12 on 13. What's x over r? Well, my x value is negative 1, over my radius is 13, so it's negative 1 on 13. Tan is x over y, well that's negative 1 over 12. Okay, so this has introduced a new idea because now we're getting some of our results are positive and some are negative. Okay, sine theta here was a positive, cos theta was a negative, tan theta was a negative. Think about, we'll do this in like our next exercise, but think about why sine theta here had to be a positive, and why cos theta had to be a negative and tan theta had to be a negative, and why for any angle in the second quadrant, in this quadrant here, that's always going to be true. Okay, don't worry about it if you can't come up with an answer to that, but have that question cook away in the back of your mind, and when we come around to do either the next or the exercise after that, we're going to look at why this is the case and see how we use that to our advantage when we come to solve trigonometric equations down the track. All right, guys. Look, that's more than enough for exercise. Let me see, 5D in the Year 11 Advanced Mathematics textbook, or 6D in the Year 11 Extension 1 Mathematics textbook. As usual, get in, have a go, get some questions done, find out where you're struggling, and make sure you ask me plenty of questions about it. Thanks a lot, guys. Good on you.